Okay, so question 5b requires us to do an ice table. Ice tables you know about. Only this is going to help us do a little assumption that we're going to apply to all weak acid situations. There's an actual rule, but you don't really need to know that rule for 10:30. So in the interest of time, we are going to make a very big assumption. And if you take it at university, when the professor tells you the rule, pretend you know, okay? All right, so the acid 2,3-trichlorophenol, phenol, what's phenol again? A benzene ring with an OH attached to it, and then 2,4,6. Trichloro. 3 chlorines on 2, 4, and 6, where carbon 1 is the OH. So could you draw this? Yes, you could. Okay. So that might be in a multiple choice, or I mean a diploma question. They might have that as the introduction. Question, 22 is what is the correct structure for this molecule? And then question 23 is which is the correct appropriate equation? And question 24 then is this. Does that make sense? How that one question becomes sort of 3. All right. So write an appropriate equation for the ionization of that. So the ionization then is, you going to do it for me? Not really. Good. So there you go. Here's your OH. Here's 2, 3, 4, 5, 6 trichlorophenol, and you are writing ionization equation. So what do I have to react it with? Water and equilibrium arrows, and I'm going to get H3O plus. What makes you so confident you're going to make H3O plus? Because it calls it an acid. Okay? Because right now you're out of your comfort zone with this crazy molecule. But because it says acid, you're going to make H3O plus. If it's at a base, you're going to make OH minus. So that means that this guy has to become OH minus by giving a proton. Right? But it says acid, so it must be taking a proton. Oops. Okay, and then the remaining structure is that with the O minus and still your chlorides there. Okay? Okay. So, the end. Done. Done, done. B. A 0.1 aqueous solution of that original alcohol is a pH of that. Calculate the Ka for this weak acid. Okay, so Ka isn't in your data booklet for this one. That's why they picked such a crazy one. They want you to calculate a Ka. So in interest of not writing that all over again, you might want to just call this A. Pardon me, HA is always best, and then this is A minus, just like we do for our normal acids, right? So I'm going to set up an ice table where I've got HA, water, H3O plus, and A minus. And this would apply to any acid. And I need an ice table, ICE, so that eventually I can plug that Ka into the A minus, the H3O plus, and the HA. Everybody okay with that? All right. So in our ice tables, this is a bit of a review, okay? This part here is a review, I hope. In our ice tables, we would say that we started with a concentration of that. So this is 0.10. Yes? The water is in excess. I got lots of it. So I was going to have as much as I need. How much will I need? 0.10. But I have more. I've got as much as I want. But it doesn't really matter because it's a liquid and it's not in our table. Does that make sense? So I don't really need to worry about it. I don't need to do it in the ice table, but you can if you like the consistency. The H plus concentration is initially 0, and the A minus concentration is initially 0. The change is where we worry about our ratio. 1 to 1 to 1 to 1. That's all in the change. Do I know how much it's changed by? No. What other information have I been given? pH. What can you do with that pH number? Right. Concentration of hydrogen equals 10 to the power of negative pH. That's a formula from Science 20, Chem 20 I mean. And so this is 10 to the power of negative 3.55, which I could type in my calculator and get lots of decimals for. Okay? So that number goes where? What's that the concentration of? What's that the concentration of that I've just saw?
H plus.
H plus. And then where on the ice table does it go?
H3O.
The H3O in my I, my C, or my E? My E. So 10 to the power of negative 3.55. So that means my change was also 10 to the power of negative 3.55. For
Acid.
no? Oh yes, well yes. Okay, so that's how much this changed by, that's how much I made. I would have also made the same amount of this. Are you okay with that? Because it's a 1-to-1 for every one I make. I'm not making a line. And this would also be, I'm going to use up 10 to the power of negative 3.55, and I'm going to use up 10 to the power of negative 3.55.
How do you know that the 10 to the negative 3.55 is an equilibrium from like reading?
How do you know what, sorry?
How do you know that
That this-
concentration goes in the equilibrium and not the change
Because this is the pH of the solution
of like the
when it's in
final
equilibrium.
solution?
Yeah.
So you know because it says aqueous solution. Like the solution has that pH.
I know because it must have reached an equilibrium in order to have my H3O plus. Yeah. Okay. And then this is 0.1 minus 10 to the power of negative 3.55. Can somebody do that for me on a calculator? Sorry?
The 10 to the power of negative 3.55
Yeah.
is 2.18.
But is that 0.1 minus? 2.18
2.81 times 10 to the negative 4.
times 10 to the negative 4. Okay, and is that 0.1 subtract that number?
And that one's just
Okay, so what's 0.1 subtract 10 to the power of negative 3.55?
0.0997.
0.0997 what?
1/8.
1, so we'll stick with 7. And this will also be 0.997. And this is 10 to the power of negative 3. What did you say that number was? 2.82 times 10 to the power of negative 4.
Yeah.
And yes?
It's 0.0997.
Sorry, yes, that sounds a bit better.
How do we get different numbers for the equilibrium on the?
I didn't, I just typed it in my calculator.
Oh, okay.
10 to the power of negative 3.55 is that number. Not different number, it's just differently communicated. And then you plug all of those values into here and you get a Ka value. Everybody get that? That is review. Do you know how to do that? Please nod your head and say yes. It's a tricky question. I'm not pretending it's not tricky for your, 5th ice table you've ever done. But if you are capable of doing that. Hands up if you think that you are capable of doing that. Okay, that's good. Okay.
Sorry.
Yeah.
You said those numbers are the same as
Yeah.
10 to the okay.
Yeah. It's always best to play along on your calculator so you know, then it makes more sense to you. Okay. Now the reason why I did this for you, number one, because it's a tricky ice table. The only thing that makes it tricky is that for a new bit, we've had to go from our pH to our H plus at equilibrium. And then plug that in. That's like the only extra step we've had to do. Okay? That's the only tricky bit of this ice table. Other than that, it's the same as the ice tables you did for your quiz, which I haven't finished marking. Okay? So, here's the point though I wanted to make. How many significant digits do we have?
3.
2. 2. 2 significant digits. Can you round that equilibrium concentration for me to 2 significant digits? Yeah, or 0 point, I want yellow, or 0.10. Everybody agree that that's that number rounded to 2 significant digits?
Yeah.
Huh. Huh. Look at that. It's the same number. Because I'm changing the value to 4 decimal places along, it rounds to the same value. The fact that this is such a weak Ka, such a small Ka value, means that the equilibrium lies heavily on this side. Meaning very, 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 very little of it dissociates, or ionizes, pardon me. Meaning this remains relatively unchanged. Okay? So this is the assumption we make, which has a big long rule and a big long discussion, which I'm skipping over. If your Ka is really small, this question you didn't know if your Ka was very small, so you had to do it. But where do you know if your Kas are really small? In your data booklet. So if you're using a Ka from the data booklet, and it's really small, here's the bit where I'm skipping over. It'll always be really small for Chem 30. Okay? All your Kas will be really small for Chem 30. Okay. That's not true for all Kas, but it's true for Chem 30. Okay? So there's a big discussion that goes with it. There's a rule that you have to apply to, but hey, we're just going to go with that. So in Chem 30, your Kas are all really small. Therefore, you can assume that this change is basically nothing. So you know those equations where we have to put an x, and an x and an x there, or 2x's there sometimes, or whatever, right? We are going to, and then sometimes you're going to end up with a quadratic. Have you done a question yet that ends up with a quadratic? Right. So that's the proper way of doing it. And in university, you are going to have to do that in the first year. However, in Chem 30, it is possible that we have Chem 30 students in the province that are taking Math 33. It's possible. It's not very, it's not a very smart way of doing it, but it's possible. You could do those 2 pathways in the Alberta curriculum. So they can't expect a quadratic. So they're not going to make you do a quadratic. So they allow you to assume that that change is negligible, which takes an x out of it, an x squared out of it actually, which removes the quadratic. So if you find you're on your way to making a quadratic, that's because you forgot to make the assumption that there's no change to the initial concentration of your acid. Okay? Does that make sense? So we're going to go down to question 8, as promised, and that is going to have us make this assumption. I think question 7 makes an assumption as well. Is that true? Question 7 you need to make the assumption for in 7b?
Yeah.
Okay, so question 8. Construct an ice table for the reaction of benzoic acid with water and develop the expression of Ka consists of the variable x. Okay, so here's benzoic acid. Remember that? And your water. And because it's an acid, you're going to make H3O plus. And what's left over is that. ICE. Okay? So the initial concentration of the benzoic acid is 0.1? No, 1.0. The initial concentration of the water, we don't need to worry about. Skip over it. Waste of time. The initial concentration of H3O plus is 0, the initial concentration of the benzoate ion is 0. In your change line, you are worried about the ratio. Okay? So if I make X amount of this, I will also form X amount of that. Does that not make sense? You take this, you break it up into 2 bits. I better get one of these bits and one of these bits, not 2 and 2. So if I get X amount of this, I should get X amount of that. Simple. Okay, so it makes sense. It looks weird, but it makes sense. And we're going to assume here that there's, what are we assuming? No change.
Sorry, why do you assume that?
Because we know it's going to change, but it's going to change to the 4th or 5th decimal place.
Oh, it's just gonna stay really small.
Right, so 1 minus 0.0008 is still going to round to 1. It'll be 0.099999, whatever. I can't remember what I even said, but anyway, 9992. And that still rounds to 1.0. So what was the point? Did you get it? And it has to do with a ratio. It has to do with how big this is and how small the Ka value is. It does have to do with a ratio, but that's the university. It's a discussion we're supposed to have here, but I mean, you don't need to know it because it's always going to apply to all of your weak acids. Okay? So you assume there's no change there. So what is the equilibrium concentration then? 1 minus, assuming no change, is still 1, because there's no change. What is the equilibrium concentration of this?
0
Pardon? 0
plus
plus x, which is just x, and here is x. Now, for every single acid, weak acid, these two will be the same. Because it's always one proton that breaks off and the extra bit. It's always 1 and 1, right? So it's always x and x for a weak acid. And you always assume no change for every weak acid. So your K expression, for Ka, remember how it's A minus H3O plus all over HA? Do you remember that that's like the help me out here? General equation for all weak acids, for all Kas. What's A minus and H3O plus in this instance? X, and they both are X, and I'm going to get the same thing each time. So these are always going to be X squared. Or if it's giving you a pH, you then take the pH, you find the H plus concentration, and you plug that in there, squared. Always. My point is, there was no point in me doing an ice table. Do you see how the ice table hasn't really filled in much for me? Is it like a long-winded process to get me nowhere, really? I could have said, well, all weak acids are going to form the same amount. That goes up there. And all weak acids, we assume, don't change. So that's still the original concentration down there. Do you see how I could have got this expression directly from that sentence without doing an ice table? So now you can do that from now on. Yes, Rachel?
So if you had a different original concentration of your acid, like if you had 2, you just have to put the X squared over 2 or whatever? Like,
Correct.
okay.
Correct. So Rachel's saying, what if they said ice table for another weak acid, 2 moles per liter, develop the expression, it would be 2 moles per liter, X squared divided by 2. Okay, now how about this one? How about this one? Let's go back to find an extra piece of paper somewhere, or like in the back of the sheet or something. And I'm going to go up to question 5 again. Oh no, I can't go up to question 5.
Did you end up subbing the value in for X then?
Not always. If it says develop an expression, we've developed the expression.
Mm-hmm.
Do we have a Ka value for benzoic acid in your data booklets? I think we do.
Yeah.
Do we?
6.3 times 10 to the negative 5.
So Ka equals 0.3 times 10 to the power of negative 5. Is that right? Is that what you just said to me?
6.3, sorry.
Okay. No, it's okay. I was like, it doesn't. Okay. 6.3 times 10 to the power of negative 5 is the Ka of benzoic acid. So a new question. Find the Ka of benzoic acid. So what is the pH of that? Okay, so same question, only now they've said, not develop an expression, but rather look up the Ka value and tell me the pH. So you're freaking out, and I'm going, no, just go like this. Ka equals A minus H3O plus divided by HA. That's the expression. Ka is 6.3 times 10 to the power of negative 5. A minus and H3O plus are going to be the same, so I'm going to call that x squared. And HA, even though that's the initial concentration, we can still assume no change. So I can put the original 1.0 down there. So multiply 1 by both sides to get rid of that 1. So 6.3 times 10 to the power of negative 5 equals x squared. So the square root of this now is what? Somebody? Pardon me? Pardon me?
7.9 times 10 to the negative.
Okay. And can I get the pH from that? Yeah.
Do we get all those equations or do you have to memorize
I
them?
memorize them all. Everything that's in your data booklet you get. No extras. And so plug that in here, and your pH is
2.1.
2.1. Is that? You get it? Lindsay? So, it looks like quite a difficult question, but actually, it's quite easy. As long as you have memorized that, and you know that those will be the same, it's a matter of quite easy plugging in numbers.
Would you ever have like a different ratio with the
Acid?
products? So that it would be like one of them is like
No.
A minus squared and the other one's just H0 plus?
Never for acids, because you're always giving up one proton at a time. So never for acids, or bases. Never for the acid-base equilibrium,
Okay.
okay? Never for Ka, never for Kz. Is everybody cool with that? Okay, so that's yesterday's finalization. Any questions?